All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Let's jump into it, and we are good. Hopefully. There we are. Okay. All right, awesome. So some announcements before we begin. Check your grade scope. Make sure everything is correct there. So hopefully everyone's aware we did have a test last week and it's already been graded. I graded it on, I think, Saturday. So you had until Friday to finish it, and I graded it on Saturday. And I sent out an email telling you how it was graded and that you should look through it as well as your general grade book. So I'd say be sure to actually test your go through your tests on Gradescope. For every problem, there's like a rubric that tells you how it was graded, what you could get points for, what points were deducted for, that sort of thing. And so you can see not only your grade, but exactly why you got that grade. And that is true for all the problems where you had to show your work. For the other problems, obviously, it just gets it, it grades it based on whether you chose the right response or inputted the right answer or whatever. But be sure to go over all of those. And also, so if there's a mistake, you should let me know by doing using the regrade request feature, which I think it's like the bottom right of the page. There's like a green button that says regrade. If you think there's a mistake somewhere, you can click that button, type a comment, and let me know what the issue is that you want me to look over, and you would do that. I think so far only one person, so several people have viewed their test, but only one person actually submitted regrade requests. And yeah, I already dealt with those, but it also brought up a problem, which there was one problem where you had to input several answers for that one problem, like an overestimate, underestimate thing. And so I didn't put in a rubric for that because I figured the computer would just like count how many you got correct and grade that. But it turns out the AI just made up its own rubric and kind of graded it like an all or nothing thing. And so that person who let me know about that issue is what notified me. Like if no one said anything, like I wouldn't even know. It is to your benefit to actually look through everything and be aware of why you're getting the grade that you're getting. And just being aware in general is a very important thing. So, I mean, any single thing in the class that is really important and would affect your grade, like I have told you in multiple ways, like it's chances are it'll be in the notes, it'll be in an email, it'll be in the syllabus. I would have said it in class. The class is recorded so you can watch it. You miss important opportunities and important informations if you choose to not be aware of what's going on. So be sure that you're looking through everything, making sure there are no errors. If there are errors, let me know, because you never know, you could be leaving points on the table. So because of that one person just looking over their work and you know, making sure that the computer was grading it correctly, you know, it gave a bunch of people a few more points on their exam that they wouldn't have gotten otherwise if no one had checked anything. So be sure to check everything, make sure it's okay. And yeah, that goes for your test as well as just your grades in general. So I uploaded a bunch of grades. I think the only thing missing at this point is just a few attendance grades. But I put in enough attendance grades to see, for you to see on average. Most people were here most of the time, so you should have close to 100% for attendance. Another thing, I did mention this in an email, but I gave everyone 100% for homework automatically just to give you like, look at what your report card would be, assuming that you did all the homework. Technically, the homework isn't due yet. So Not everyone has 100% on homework at this point, but I'm just saying the grade you're seeing now is kind of what your current grade would be, assuming that you did all the homework and you got at least 90% of it correct. So make sure that that actually happens, because when the actual homework deadline has passed, which happens on August 2nd or something like that, your real homework grade would come in. And if you didn't do all your homework, that's going to drop your grade more than it is now. But generally speaking, I think getting 100% on the homework shouldn't be too difficult a task. So, and it's less than the minimum amount of work you should be putting in to this class anyway. So you just get that out of the way, and that gives you almost 1/5 of your grade. So it's nothing to scoff at. Just try to get through the homework. So that being said, your overall grade is there on Blackboard. Now, one thing that I just changed today, again, because someone looked through everything and brought it up to me, is I believe up until yesterday, or even earlier today, like when you went into Blackboard to check on your grade, like you saw the numerical grade, it turns out that the things are actually graded on a curve. So your numerical grade might not translate to the letter that you're thinking. And chances are the letter grade is slightly better than that. And the letter grade is the one that I would be entering on your report card. So the numerical grade is a few points shy of what is actually going on, I think. So I since then changed that to make the letter grade the primary thing that you see when you log into your report card. So I changed that very recently. So some of you might, do well to look over that as well. What else do I want to see? Yeah, so I mentioned that as well. Okay, so the last day to apply for a W grade, which means withdrawing from the class, as well as like a pass fail, is tomorrow. So pass just means you get a D or above, and you would get a P, and fail would mean you get a D or below, and so you would get an F. And so there's no letter, it's not a GPA, it doesn't affect your GPA, it just says whether you passed or failed the class. If you're going to that option, I would say to make sure that that is okay, because sometimes depending on the major, they might want to see a letter grade, and it's not good enough to just have a pass. I think for some of you, especially if you're trying to take this class for fun, quote unquote, or maybe even as a minor, that might not be the case. But I would definitely talk to an advisor who knows that for sure before actually making a decision. So some of you might not want the stress and just be like, okay, I'm just going to do it pass fail instead of like worrying about whether I got a B+ or an A- and not have to sweat it. So that tomorrow would be the deadline for that. But make sure you understand all the repercussions before actually doing anything. And if you're actually thinking of withdrawing or something like that, you probably should talk to me, because like I said, it is possible that you're in a better situation than you think you are. It's possible. So I would say you should definitely talk to me before you think of doing anything of that sort. But yeah, so in general, just make sure, look over everything, make sure everything is roughly correct. Make sure that every time I marked you present, you're present, and I didn't mark you absent when you were present, things of that sort. Because sometimes I've noticed, like, there are times when students have like internet issues and they might drop out of the class and come back. I might have taken attendance when you were dropped out, but you were actually there that day. So things like that, you should look over and make sure I actually marked you correct. I think generally that's it. Another thing I would probably say is that theoretically, in theory, it's still anyone's game. Anyone can still get an A if they work hard. It's a matter of how well you do on the remaining exams. So keep your homework grade at 100 and do well on the second test and the final. And an A is still within reach for pretty much everyone. I think the class average is around a C++, ish, that area, which is typical. And I don't think anyone's currently failing the class. So I think the lowest grade is a D, and I probably have only a couple people getting that at this point. But I would say it's still anyone's game, provided that you can actually put in the work to make up the difference with what we have remaining. So that being said, I think we can continue unless there are any questions or concerns or any issues, like of a general nature as opposed to, specific. Yeah. So again, I mean, it's not required, but I would prefer if you have your cameras on. I would also prefer if you guys talk back to me. So sometimes, I'm asking a question and it gets very silent, and it's like, so one might think by like watching me that, what, Jhevon must like awkward silences. Like, that's not the case. I don't. So here's the thing. One of the things, and it's something that you might not realize, but it is true. And so I'm going to tell you, it's actually important for you to like verbalize what you're thinking. And to me, it doesn't so much matter if it's right or wrong. So don't just feel like, oh, if I don't know what the right answer is, like I can't say anything. Like, it's okay to actually say, oh, I think this would be the answer, but I'm kind of confused about this, or I don't know what. That's fine. Like, if you guys already knew everything, you probably wouldn't be here. Like, I'm not under the assumption that you all know everything and everyone will always have the right answer to any question I'm asking. The point is, well, twofold. One, for me to know where the class is and what everyone kind of is understanding from what I've said so far. And two, is just to actually get you to talk about it. So there's actually a very deep connection between your cognitive performance and your language. And it turns out, and again, this is something that's very, like, it's not exactly obvious unless you actually start thinking about it. But the more you're able to actually talk about something, the better you are with that thing, cognitively speaking. So in theory, if you were to change nothing, like you study the same amount of hours, spend the same amount of time on homework, and do everything the same, except you would speak up in class and start to verbalize more, your grade would literally go up because of doing that. Like, it's actually a big deal. I'm not going to say it's going to take you from a D to an A, no, but it'll bump you up like a half a grade. Like, you can go from a B to a B plus just by trying to verbalize something. And there were experiments done that kind of show this, when if you kind of mess with people's brains to the point where it kind of messes with their ability to use language, you can show that they can take very simple tasks and then they suddenly can't do it anymore because they can't verbalize it. And so being able to talk about something is actually very important. You will actually start to understand it more just by talking about it. So me trying to get you guys to talk about stuff and me waiting to try to get a response, it's not just to waste time. It's important for you guys to talk back to me. So I would appreciate it if you would. What else? Yeah, and also take the opportunities to see me during office hours if you want to talk about anything or anything is off. So yeah, so it turns out I noticed this with a couple students, and I actually also noticed this with just grading. So someone mentioned asking for more time. So uploading, there's a quick way to upload, and it's usually from your phone. And so I would recommend that you actually, and this was one of the point of the practice test, actually practice uploading, because it is possible to upload relatively quickly. And more time is probably not what I would do at this point, because technically you have been getting more time. So I have taught this class online prior to this, and I'm giving you guys more time technically than I did the last give the last class. So it's an issue with how you're uploading. And so I would recommend that you kind of, one, if it's actually slow uploading from your phone, probably you need to fix your resolution. But secondly, if you're not uploading from your phone, a lot of people told me they had to go through their laptop to upload something. That should not be the case. Like if you have a smartphone, you should be uploading from your phone. It's much quicker. It will take no time. Because in the end, even if it takes a few seconds or a minute to upload, like when you're uploading for one problem, you could be working on another problem. So if you're doing it right, uploading should not take you more than 2 minutes after you finish the exam. It's not something that should take a while. And at this point, I'm giving you guys 15, 20 minutes more than should be required technically. And I'm giving you that because, you know, in my mind, it's because of internet issues. If you get kicked off the internet for a while, you have like a cushion to get back in. But uploading shouldn't be too costly time-wise. So if that is costly, it's something that you're not doing efficiently and probably need to talk about. You probably need to practice on a practice exam, or if you believe you're doing it as fast as it can possibly be done, we can talk about it. And that's sort of something to discuss in office hours, I would say. What else? I think that's sort of it. So we've actually done, if you have any more questions or concerns, you can let me know. But I think those are all the announcements I wanted to make. But for now, we are going to review what we did last time. So last time we actually finished all the series tests that we want to do. So we had a table, and the table was in the previous lecture, I believe, and I actually recopied it in our lecture today. So I had this table that spoke about all these series tests that we want to do. So remember, there was a notion of a series converging, that an infinite sum actually adds up to something meaningful. The technical definition for this is the limit of the sequence of partial sums. But as I mentioned, finding that and then finding its limit can be very difficult to do in the best case scenario. And then even if you could do this, it can take a lot of time. Sometimes it's not even possible at all. So there are times when we would rather just know that a series converges at all, as opposed to knowing specifically what it converges to like exactly. And so we invented these things called series tests, where we can know that series will add up to something meaningful, even though we might not know exactly what that thing is exactly. And you might be worried, well, if we don't know what it adds up to exactly, how is that any useful to us? And we'll actually deal with that question later today. We're going to talk about how is it useful if I know that it adds up to something, but I don't know exactly what. We're going to actually deal with that. But these tests were to answer that question. How do I know that something converges, even though I might not necessarily know what it converges to? There is one test, which was the geometric series test, which does actually tell you exactly what something converges to. If something is a geometric series and it converges, then I know exactly what it will converge to, a over 1 minus r, where a is the first term and r is the common ratio, that thing that you keep multiplying by to generate new terms of your the sequence that is being summed by the series. Otherwise, none of these tests really tell you what it converges to. They just tell you that it converges. And in the kth term test, it also doesn't tell you that it converges. It only tells you that it diverges. It potentially can only tell you that. Sometimes it can't even tell you even that, but those were the tests. And we went through all of them, and we did a few examples to show how they all work. Awesome. So we did that. And then there's going to be the notion of absolute convergence, which I think we also spoke about. Oh, I'm in the wrong lecture. So this is last lecture. And in the last lecture, after going through the remaining of the tests, which the last one we did was the root test, I believe. And into the alternating series test, ratio test, the root test. Yeah, there's this notion of absolute convergence, which I gave you guys this schema for determining. And so we also spoke about the idea of the different types of convergences for series. There is converging absolutely, or absolute convergence, and there's the notion of converging conditionally, or conditional convergence. And basically what that means is absolute convergence is if you go to the sequence and you put absolute values around every term, so there are no negatives. You're adding up the magnitudes of everybody. And if that series converges, then we say the original series converged absolutely. It converges even if we put absolute values around all the terms. If that series doesn't converge with absolute values, but if I take the absolute values away and look at the original series, that guy converges, then we say it converges conditionally. And it's actually important that we know what kind of convergence is happening, because a lot of things we want to do in calculus, like differentiating, integrating, taking limits, they do not work if we have conditional convergence. A conditionally convergent series is almost as nonsensical for what we want to do as a series that diverges. So absolute convergence is the nice one. It's the gold standard. It's the one we like. When something converges absolutely, it means we can actually treat that series as a bona fide mathematical object. We can do math with it. We can do arithmetic. We can do calculus. We can do a lot of things with that infinite sum as if it were just a regular function. And that idea we're actually going to talk about more, like looking at series as functions. But yeah, so we looked at the process for doing that, and we're going to do, today we're going to start by doing some examples of this, examining a series, not just for convergence, but for whether it converges absolutely, conditionally, or diverges. Okay, and I put some notes here about that. And usually the kind of problem that you would want to consider this for is one where I specifically ask you, determine whether it converges absolutely, conditionally, or it diverges, right? So there's a problem type where it's like, I just ask you, does this converge? Or what does this converge to? And there's also a problem type where I would ask, does this converge absolutely or conditionally, or does it diverge, right? So once you know you're looking for absolute convergence versus conditional convergence versus divergence, this is the process you want to go through. So it's not specifically a test, it's more of a method that you go through to make sure that you can distinguish between the two kinds of convergences. So, step 0, which is, I would say step 0 in general, is to always try to apply the test for divergence first, because it's going to be the easiest thing to check, usually, because it comes down to just taking a limit and seeing if it's 0 or not. A lot of times you can even eyeball this, and you would just, but based on the functions that show up, you'd be able to, well, obviously, and you can do that very quickly. And if it's inconclusive, you didn't lose a lot of time actually checking. But if it is conclusive, then you can potentially save yourself a lot of time working on problems. So you always check the test for divergence first. Remember what the test for divergence is. You take the limit as n approaches infinity of the an term, of the sequence term. And if that equals 0, if that's not equal to 0, then that means the series diverges. And that is the only thing you can conclude. And that is the only situation in which you can make a conclusion. Any other thing, the series, if the limit converges to something that's non-zero, it diverges. If the limit converges to something that is 0, you don't know. You cannot make a conclusion. That's it, right? So if the limit approaches 0, you can't make a conclusion. But if the limit does not approach 0 or it does not exist, you can make a conclusion. And you can only conclude divergence from the test for divergence. Okay, so assuming that you can do that and you can determine that something diverges, then you're done. Like, you just say the series diverges and you move on with your life. Okay, but let's say you get the limit equals 0, which means it's inconclusive. Then you can move on to step 1. So step 1 basically says you always check absolute convergence first. So if I give you a series, you tried the test for divergence and it doesn't work, the next thing you're going to do is you're going to put absolute values around all the terms, not around the whole series, around each individual term in the series, and then check if that series converges, because this can get rid of negative signs. It can do all sorts of things just to measure the magnitudes of the things you're adding up. And then you can do a test to see if that series converges. Now, if that converges, at this point, you can say, all right, the series converges absolutely. The original series converges absolutely, and you can stop the problem there. Now, if you put absolute values around everything and you do a series test and the series test says, oh, it diverges, then you're not done. You have to move on to step 2, which is to check, does it converge conditionally? So now you're going to take the absolute values back, right, and look at the original series and then check a series test to see if that converges. And if that works out, you say the series converges conditionally. If that doesn't work out, then you can say the series diverges, and that will be done. So there's kind of like a three-step process where the first step is kind of like not even a full step. It's just like a quick check to make sure that you're not wasting your time by doing the 2 steps required for this problem. So you always check absolute convergence first. You check conditional convergence if it doesn't converge absolutely. And if it's shown to converge conditionally, you say, hey, it converges conditionally. If it doesn't, you say everything diverges. Remember some of the nuances of the test. The geometric series test is the only test that can tell you exactly what something converges to if it converges. You can also determine exactly what something converges to if it's telescoping. We looked at an example of that. Those are pretty much the only 2 cases where you can tell exactly what something is, other than if we're in a situation of power series, but we'll talk about that later. The divergence test can only tell you about divergence. It cannot tell you about convergence. So that's another thing you have to be aware about. And another thing that we need to be aware of is the alternating series test it only works on alternating series, and it can only tell you about conditional convergence. What other nuances were there? The ratio and the root test, they behave the same. So if you do the ratio test and it was inconclusive, the root test will also be inconclusive, and vice versa. So you only, if you're using one of these tests and you can bring that to completion, you don't have to try the other one. I would try a completely different test. I think those are all the nuances. Other than that, everything you need to know about checking for series convergence is in this table that I'm showing you, or the table that I had last time, or this table. So when it comes to series convergence, this table is important, and this table is important. And this table is only important if I ask you specifically to talk about absolute convergence versus conditional convergence. Okay, so that's kind of just summarizing all the things we know there. So this part of, and I guess a little bit about what we're going to be doing later with series, but this part is specifically kind of has the same flavor as doing integrals. So the idea is you're looking at a random series and you want to determine whether it converges or diverges. It's a matter of using the right test. So you have a list of 10 things that you can try to determine what's going on with this series. Like, how do you know which thing to pick to use on the series? We're actually going to talk about that, but that's a part of the game, just knowing when to apply which method. And we'll actually talk about that as well. But let's actually do some examples of this process, determining absolute convergence versus conditional convergence versus divergence. Okay, so here you see the example, and it's worded as you might see. Determine with justification whether the series absolutely converge, conditionally converge, or diverge. And here is the first one. So, you know, this is the problem that you want to do. Okay, how do we actually go about one second. Okay, so how do we actually go about doing that? So like I said, there's a 3-step process. So the first thing we're going to do, I'll just show you an example with this. First thing we're going to do is we're going to try the test for divergence. Okay. Because if that works out, that's going to be the quickest thing to actually verify. So we're actually going to look at the limit as n approaches infinity of cosine squared n plus 1 over n squared plus 1. And what is that in this case? What's that limit? What's the biggest the numerator can be? Let me ask that.
1.
No. Oh, by the way, make sure you're reading the notation correctly. That's the only thing that's in the cosine. Right? So the 1 is not in the cosine. So what's the biggest the numerator can be?
2.
2. That's the biggest, right? What's the biggest the denominator can be? Right, someone did this. Like as big as you want, it goes off to infinity. So you have a fraction where the biggest the top can be is 2, and the denominator is going off to infinity. What's the limit? Right. See in the chat, 0. 0 is going to be that limit. So what does that mean for the test for divergence? It converges, right? So 0 means inconclusive. You can't say anything. Okay, so test for divergence didn't help us here, but in theory, this should be something that shouldn't take a long time to check. Your cosine, you know, the biggest it can be is 1. So the maximum this is like 2 over n squared plus 1, which obviously goes off to 0. So it's very quick to see that this limit would go to 0, but it doesn't really tell us anything. If it was not 0, we would be done with this entire problem. We would just be like, this thing diverges, and then we move on. But in this case, it's 0, so we can't really say anything. So you move on to the next part. And so now what you're going to do is you're going to check absolute convergence. Now, what does it mean to check absolute convergence? You are going to check whether this series was n goes from 1 to infinity. You're going to put absolute values around each of the terms. And then you're going to look, does this new series converge? Okay, so that's what you're going to look at, right? So if I pretend all the terms are positive, right? Which, by the way, in this case, now note, I was going to make a comment, but I guess I'll make that at the end. If we're looking at this guy, remember, a nice thing about trig functions is that, especially when you put absolute values around them, they kind of already invoke this kind of inequality. And as long as you're not like a tangent or a cotangent, this could be something that's useful. Because you can bound a cosine. So we know that, for example, like a cosine is between -1 and 1 always. So that sort of means that if I squared everything, your cosine squared is going to be between 0 and 1. So we can automatically make that bound. And so this would mean that if I take cosine squared n plus 1, that's automatically less than 2. Right? So this is going to be a value between 1 and 2. Okay. And so this kind of feeds into the question that I asked you earlier. What's the biggest this could be? And we have that. So in other words, I can actually create an inequality here and say this will have to be less than or equal to this series. Whatever value it's giving me, it's going to be less than or equal to the value of that. And now I can actually go further here, because I could make the denominator of this one smaller, say n squared, and it's going to be less than that. So ultimately, the original series I gave you, in absolute value, it will be less than that series. Okay. Now, what can you tell me about this series, 2 over n squared? What kind of series is it? Has a very specific name.
P series?
The P series, right? I mean, remember, we have that property that for a series, we can factor out constants, right? So the two shouldn't get into the way there. But this is really, you're essentially looking at the series of 1 over n squared, which reminds you of 1 over n to the p, which is a P series. Does this P series converge? Yes or no? Yes, because P is greater than 1. Okay, so this is a convergent P series. Let me. So in absolute values, our original series is less than or equal to a series that we know converges, which means I would be able to make a determination on this based on comparison. So this means that this series converges by comparison. Now, what does it mean that this series converges by comparison? Now, this series is our original series with absolute values around it. So that means our original series cosine squared n plus 1 over n squared plus 1 converges absolutely. Absolutely converges. And we use the comparison test to do this. Okay. So if a series converges when you put absolute values around it, you say the original series converges absolutely. So this series is like a bona fide sum. It's a concrete mathematical object. We can do calculus with it. We can do all sorts of things with this guy that we wouldn't be able to do if he wasn't absolute convergent. Okay. So here is a process for which we needed 2 of the steps. So you do a quick check with the limit to see does it diverge or not. We can only make a conclusion if it's not equal to 0, meaning if it's something else or it does not exist, then we can say, oh, it diverges. If it is 0, it's inconclusive. We have to do something else. In this case, first thing we want to do, put absolute values around it, check if it converges. If that converges, awesome. We stop and we say it converges absolutely. If this didn't work out, what I would do is I would remove the absolute values and try something else. But in this case, it worked out, so we're good. Yeah. Let's move on to the next example. And by the way, yeah, the comment I was going to make here is because we know that cosine squared is greater than or equal to 0 because it's the square of a real number, then we kind of know that all the terms here are positive in the first place. So if this converges, it would be absolute convergence because there are no negative signs to get rid of with the absolute values in the first place, right? Because the minimum this is going to be is 1 over n squared plus 1, right? It'll never be worse than that. So technically all these terms with absolute values or without, it actually didn't matter. If this guy converged, it would be absolute by default, just by the nature of the terms that we're seeing here. But it wasn't necessary to realize that to begin with. So here's one, another one, right? And it's the same problem. Determine whether the series converges absolutely, converges conditionally, or diverges. So we know the first thing we're going to do is going to do the test for divergence. which means we're going to take the limit of the an, which in this case is going to be the limit of the cosine of n factorial over n to the n. Right. So I guess I could make a note here. We can ignore the -1 to the n. And the reason is, since if I have -1 to the n times something that gives you 0, then overall the answer is going to be 0. So that's not going to stop it. And if I have -1 to the n times something that is not 0, then -1 to the n times that thing is also not going to be 0. So whether it's 0 or not is not affected by the -1 to the n. So essentially I can ignore it in the limit. It's not going to be an issue. And we also know that if we're putting absolute values around something, we can also ignore the -1 to the n. So like when we're doing the ratio test or the root test, you don't have to put in the -1 to the n in your calculations. It's not going to make a difference. In the same way, when you're taking the limit and you're just concerned whether it's 0 or not, you can ignore the alternating sign. It's not going to affect anything. So I just want to make sure of that. Now, what is this limit? Any ideas? I'll give you a hint. Cosine is a continuous function. We know that limits can pass in and out of continuous functions. This is actually something that we saw in the test. Oh, by the way, I didn't mention this in an email. When you look at the notes online, you should see these tabs over here. And if you go solutions to test, you will see solutions to the test, right? And I wrote out justifications. Even where it didn't ask you to show your work, I wrote out justifications for the problem. And I show you what, a solution would look like. So you can actually see solutions to the test. And I actually use the property that I'm currently mentioning in one of these problems somewhere. Yeah, like here, I use that idea by moving the limit inside the function. So that's what we can do here. Okay, because cosine is a continuous function, if you take the limit of a cosine, it's the same as the cosine of the limit. So that might actually help you see what this thing should go to. Right? Limits can go inside and outside of continuous functions. So that was something that you learned in Calc 1. In fact, that was kind of the definition of continuous, right? So you learn that continuous means the limit as x to the a of f of x approaches f of a. And the reason for that was because we could actually move the limit inside. And so that gave you f of a, because limit as x approaches a of x is a. So continuous functions have this property where you can move the limit in and out of them. So yeah, so if you want to know what the limit of something is and it's a continuous function, you can move it inside. So what's the limit of n factorial over n to the n? Ideas? 0, because it's bottom heavy. So someone's texting me the answers. So yeah, this is cosine of 0. Because remember, logs are much smaller than polynomials, much smaller than exponentials, much smaller than factorials, much smaller than n to the n. So n to the n is bigger as n goes to infinity than n factorial. So this is bottom heavy. Cosine of 0, by the way, is 1. And guess what? 1 is not 0. So what does that mean? Series diverges and we're done. By the test for divergence. Okay. Now, again, that is something that shouldn't take a long time. You should know that n factorial is smaller in magnitude, whatever that means. I mean, they're both going to infinity, but the n to the n will get to infinity faster than the n factorial. And so it's bottom heavy. The inside fraction goes to 0. Cosine of 0 is 1. And so, you know, we can quickly determine that this series will not converge. So that series adds up to, it's not, I guess you can't say it adds up to like, because it alternates. So it's not gonna make sense. It's not gonna settle anywhere. So we have that. Here's another example. So again, this is like another problem in the test where you can actually use an identity. Like it is something that I expect you guys to know. So there's a short way to do this problem and there's a longer way to do this problem. And so it would depend on, you know, what you see. Either way would be accepted. But there are actually a couple ways to work this out. So one is, again, we're going to do the test for divergence. So we're going to look at the limit of an, which in this case is the limit of n over n plus 1 to the n. Now, this is something that shows up, I don't want to say it like super often, but relatively often. One thing you can notice is that, well, this would be the same as, say, 1 over. So I can take the reciprocal and move this in the denominator. And you might think, well, why would I do that? It's because there's a pattern that I'm seeing. So if I see n plus 1 over n, or its reciprocal, there's always something, and it's raised to like a nth power. There's always something that I'm going to try to check that if I can use to my advantage, because this here simplifies to 1 plus 1 over n to the n. And that should actually remind you of something. So that this is something that you can use. We know that E is defined to be the limit of 1 plus 1 over n to the n. Like by definition, that's like a definition. Right. So that's how E was developed. It really comes from compound interest formula. So this was the principal, the rate divided by the number of times compounded per year. And if you let the number of times compounded per year go off to infinity, assuming 100% interest rate starting with $1, that was defined to be the number E by Euler. And so that is where the number E comes from. You can generalize this to know that E to the X it's just where there's an x in this position here, right? So e to the 1 is 1 plus 1 over n to the n. E to the x is the limit as n goes to infinity of course. Should specify it here. We don't have to specify it for sequences, but here we can specify it. So these are definitions for E. So you can know that this limit here goes to 1 over E. And by the way, that's not 0. So you can say the series diverges. So that was actually one way to do it. If you notice that, oh, I can use the definition of E here, which is something that you're always kind of thinking. If you see 1 plus 1 over n, or n plus 1 over n, or n over n plus 1, sometimes kind of trying to squeeze E into it, especially if it's like a limit going off to infinity, is something that's going to be beneficial. So that's something that, there are a few problems in your textbook where they actually use this trick and get E in there. However, alternatively, let's say you forgot what E is defined as. You weren't stuck. It would just take you a little bit longer to get to the problem. So alternatively, let's say you wanted to deal with the limit as, n goes to infinity of n over n plus 1. The first thing you would notice is that this approaches 1 to infinity, which is an indeterminate form. Okay, so n over n plus 1 as n is going off to infinity approaches 1, ratio of leading coefficients, we know that. And then it's raised to the power of n, which is going to the infinity. So this is approaching 1 to the infinity. So it's currently an indeterminate form. And we know how we deal with indeterminate forms. We have to rewrite them so that potentially we can use L'Hopital's rule. However, rewriting them can also potentially put us in a situation where we don't even need L'Hopital's rule afterwards. But if an issue is an exponential, like the 1 to the infinity, or like a 0 to the infinity or anything like that, infinity to the infinity, these are all indeterminate forms. If a power is the issue, that the power is going off to infinity, we know that we can bring it down by using ln's. So you can either do this log thing where you log both sides, you say y equals this and you log both sides, but you can actually also rewrite it on the spot, which to me is the preferred method. And you can rewrite that thing as e to the ln of that thing. Now, the benefit of that is that we know there's a log rule that says we can bring powers down and they can become multiples. So now the power isn't an issue. So now you look at the power. And remember, limits, this is, I would say you wouldn't have to write this, but you can actually think about it this way. The exponential function is continuous, so the limit I can move inside the exponential. So now I have E, and I'm worried about there's a limit in the power of E. And this one you can check. N is going to infinity, so the n part is infinity times ln of n over n plus 1. The inside is going to 1. So that's approaching ln of 1, which is 0, which is another indeterminate form. So we know from Calc 1, if you have an indeterminate form, that's a power. Use e to the ln of the thing to bring the power down. Any indeterminate form that is a product, you can use the reciprocal trick. So I would leave one of these guys and take the reciprocal of the other one and put him in the denominator. So I can write n as 1 over n. Now, if you look at this limit, the top approaches 0 and the bottom approaches 0. So L'Hopital's rule applies. And so according to L'Hopital's rule, L'Hopital, you have to say it with a French accent or it might not work. This limit is going to be the same as if you take the derivative of the top divided by the derivative of the bottom, right? So the derivative of the top is going to be essentially, it's going to be n over n plus 1. I mean, I could actually write this as I would say note, because it'll be easier to do this. Remember, ln logs of a division is just the difference of logs. So if I see ln of n divided by n plus 1, I can think of that as just ln of n minus ln of n plus 1. And so then if I differentiate ln of n, I would get 1 over n, minus if I differentiate ln of n plus 1, I get 1 over n plus 1. So that's the derivative of the top. Derivative of the denominator is minus 1 over n squared. So then I can rewrite this. So this is just minus n squared times 1 over n minus 1 over n plus 1. So that is actually, if I combine these fractions here, this is n squared plus n. And so that actually approaches minus 1. So that's also 1 over e, which is not equal to 0. So this is a little bit longer. Well, if you remember your Calc 1 very well and remember how to do within the determinant forms, will take you, 2 or 3 minutes to actually work through. But if you didn't see how to use the definition of E, you could have done that. But either way, the conclusion is the same. The series does not converge. This would be the short way to see it if you remember what E is. So here's another one. So again, apply test for divergence first. Take the limit 1 over ln of the radical n plus 1. Obviously, the numerator stays at 1. The denominator is growing without bound. That gives you 0. So this is inconclusive. So you move on to the second one. Check absolute convergence. So what I'm going to do is I'm going to look at the series n goes from 1 to infinity of absolute value of minus 1 to the n over ln of radical n plus 1. Because this was our series here. Which, by the way, it's just going to be the series of 1 over ln of the radical n plus 1. Right. So the ln for n is 2 or larger, that's always going to be positive because we know that log of 1 is 0. And any log is an increasing function. So log of anything bigger than 1 is going to be bigger than 0. So the denominator is always positive. The only thing that could possibly give us like a negative sign is the -1 to the n when the n hits an odd number. And so by putting the absolute values around it, it's just like me having this series to worry about. Now, let's talk about that series. If I look at this series, first thing I can note is that this is the following, right? The ln of the radical is annoying, but remember radical just means 1/2 power, and we have a log rule that says if you have logging something to a power, the power can come down. So I can actually put the 1/2 in front. So that's just this guy. Now, here is another crucial thing that knowing, remember I mentioned to you that this relationship is super important. Something you should always be thinking about. You're thinking about limits. Definitely it's something that should pop up in your head almost immediately. So you know that, for example, here, a logarithm is always going to be less than a polynomial of the same, well, it's less than a polynomial, just like in general, right? So in other words, this means if you ignore the ln part, you would get something that's larger. So in general, ln of x is going to be smaller than x. I mean, you can actually see this from the graph, right? So if you look at like, this is ln of x, you know, and the graph of x looks like this, passing through the origin, right? X is always bigger, right? And of course, if you have like x squared or x cubed, it gets even bigger than that, right? So your log is going to be smaller than any polynomial. And so if you ignore the ln part, you actually get something that's bigger. So what I'm going to do is I'm going to look at the series of just me ignoring the ln. Now, the denominator of this series here is larger than the original, right? If I put ln on the denominator, it gets smaller. So this means this series is actually larger than that one. So this is actually a bigger series than that by me ignoring that. But guess what? This one, the second one, is actually something that I know how to deal with, right? So this is essentially a harmonic series, right? It's just one step ahead, right? It looks like 1 over n. So this we know. This we know is a divergent because it is a harmonic. It is harmonic. Right. One way, I mean, anything that has like a linear thing in the denominator, you can consider like a constant over a linear polynomial. You can consider it harmonic because it just means you can kind of do a substitution to change it to look exactly like a harmonic series. Like, for example, if you have the series of 2 over n plus 1, this is just 2 times the series of 1 over n plus 1, and goes from 1 to infinity. And if you do something like, oh, set k equals n plus 1, right? This means when n equals 1, you have k equals 2, but then that just gives you the series k goes from 2 to infinity of 1 over k. And we know 1 over n is harmonic and it diverges. And this is just missing the first term. So, I mean, if you want, you can also see this, or you can look at this as it's like the harmonic series k goes from 1 to infinity of 1 over k, but then I subtract the first term. Either way, the first guy is going off to infinity. So this goes off to infinity because we know the harmonic series diverges, because this goes off to infinity and then you're subtracting 1. But either way, it's harmonic. So we actually know that this guy will diverge. You could also know that it diverges by the integral test. If you do the integral test on this, also, if you do the integral test on this, let me make a note that the conditions for the integral test applies, because it's a positive decreasing continuous function. So if I look at the integral from 1 to infinity of 2 over n plus 1 dn, obviously that's going to diverge because that gives you 2 ln of n plus 1 from 1 to infinity. And that, of course, equals infinity. So a couple ways you can see that that diverges. But the harmonic way is nicer and faster. So I have my series here is bigger than a series that I know to diverge. So this guy is going off to infinity, and he's actually smaller than the original series I'm looking at, which means that that series goes off to infinity. So in other words, this series diverges. Now, I want you to note, we're actually not done. Technically, we're on step 2 of this process. And remember, as I mentioned in the table, well, step 1, because we had a step 0. If you put absolute values around something and it diverges, you should actually move on to the next step. So we know that it doesn't converge when we put absolute values around it. So there's still the question of, would it converge if I didn't put absolute values around it? So that leads us to the next step, next stage, check conditional convergence. So this is an example of me having to go through all stages of the process. Because test for divergence was inconclusive. Testing for absolute convergence didn't work out. So now I'm going to see, can I get away with conditional convergence? If the test for divergence was conclusive, then I could just stop, as we did in the previous example. If the test for absolute convergence was conclusive, then I could stop, as we did in the first example. But if none of those work out, I have to check conditional, which means I look back at the original series. Now, here's the thing that we notice about the original series. It has a -1 to the n in it. And otherwise, the 1 over ln blah, we know is positive always. So this is actually an alternating series. And so, note, this series is alternating. And we can notice a few things. AN converges to 0. AN is decreasing, right? Because it's a constant on top, and it's something that's growing in the bottom. So definitely it's getting smaller and smaller over time. And we know that AN is greater than or equal to 0 for all n. You know, because we have our AN is going to be greater than or equal to ln of 2. Well, ln of radical 2. So this is radical 2 when n is 1, and then it only gets bigger because n starts counting up. So we know it's positive. We know it approaches 0 because we got that in the test for divergence. And we also know it's decreasing. I mean, technically you have to say a little bit more about that, but here it's painfully obvious it's decreasing because the numerator is constant. And so this actually converges by the alternating series test. And what that means is the original series converges what we call conditionally. I mean, you could just write the series, but I'm just writing out this formula for emphasis again. Converges conditionally. By the alternating series test. So these were a bunch of examples we did here. So sometimes test for divergence, it's a very quick thing to check, so you check it right away. If it's 0, it's inconclusive. In any other case, you can conclude that it diverges and you would just stop here. In the first case, we tested if that tested the test for divergence, we got 0. So we had to move to the next step. Put absolute values around anything. Here we could use comparison to show that it converges, therefore we can say converges absolutely. And then you're done. In this example, test for divergence showed that the limit approached 1, so it diverges, and we're done. We didn't need any other step. This one also was divergent. It's pretty much, conceptually speaking, it's exactly the same as the last example. I just wanted an excuse to remind you guys of this relationship. E is that limit. It will show up in the strangest of places. It's something that's worth remembering. So I just use that as an excuse to remind you of that. Also to remind you of indeterminate forms and applying L'Hopital's rule, because that will come up if you want to take a limit. So we did this one, and this is one where we had to go through all 3 parts of that table. So test for divergence was inconclusive. Test for absolute convergence, we actually diverged by comparison to a harmonic. And then when we removed the absolute values, you saw that this converged. So with absolute values, it diverges. Without absolute values, it converges. We say that this thing converges conditionally. Okay. So those are just some examples. So worst case scenario, you'd have to go through 3 different stages to solve one of these problems. However, if you're lucky, and chances are I will put a problem like this just to test if you wanted to know when you should get lucky, you might be done on the first stage. So we're going to take a break for now, 5-minute break, and then we'll start with the next section on just to make sure that you know my choice of tests isn't something completely random, we're going to go through just like integrals, how you would approach a series, know what test to use, know what to check and when. So we'll do that when we get back. So take a break, stretch your legs, and we will return in a little bit. All right, we are back. Let's continue. By the way, okay, no problem, Daniela. I posted a link in the chat. It's to a Radiolab podcast, which I think, generally speaking, is a nice podcast to listen to. I really like the production value on it, and their topics are very interesting. But it's actually an old episode on words where some of the things I was talking about was brought up. And, you know, a part of it, there was a story in there about a guy who had a stroke, and it actually wiped out the language center of his brain. Like that part of his brain just didn't function anymore. And it spoke about the challenges that he had, as well as some experiments that they actually did with this, and sort of tried to figure out like what exactly is the connection between language and your cognitive abilities. And they're deep. It's funny the kind of experiments that psychologists could have gotten away with back in the day. Like some of the experiments they do were like not ethical by today's standards, but you know, we got some good information out of it. But yeah, there are times when even you think in terms of language. So trying to disconnect the two, you actually are at a very big disadvantage. So yeah, you want to get better at something and understand it better. Start talking about it more. It actually will help you understand that thing better and quicker and more clear. The moment you get it into the language center of your brain can actually do a lot more with it than normal. So it's not just a matter of being shy, like to not talk up about something, or if you don't understand something, to not try to verbalize it. You're actually putting yourself at a disadvantage when it comes to actually learning it. And it's something interesting. It's something that I also noticed, like when I was, you know, back when I was a little Jhevon and I was like a tutor, something I would notice is that when I was like tutoring someone and, you know, there was a point where we had to do some arithmetic calculation to move on, I would always notice that the person would mumble if they weren't, if English wasn't their native tongue, they would actually mumble calculations in their original language. So they'll be mumbling arithmetic in Spanish. And I always, you know, so we're talking English. And then when I asked them, oh, what is this? And they would calculate it, I would hear them mumbling in Spanish. And I always thought that was interesting. But then I was like, oh yeah, it makes sense. Like they think better in Spanish, right? It takes time for them to actually form an idea in English. And so yeah, it literally, they think faster, they think better when they do it in Spanish. And so whenever they had to go do a calculation and they didn't have to talk to me, I would notice they would think in Spanish as opposed to English. And I always thought that was curious, but then it started to make sense when I think about it. Like you can't really think without language, or it's very difficult. But yeah, so that might be interesting, an interesting listen. Just in case you want to know more about the kind of thing I was talking about. But without further ado, that's not why we're here. This is a math class. We should talk about math stuff. So let's continue with that. So we're going to look at a strategy for when to use which series test to kind of figure things out. So just like with integration, we learned a bunch of methods of integration. And one of the main challenges was knowing when to do what, right? When do I do a substitution? When do I do integration by parts? When do I try a partial fraction? When do I try a trig sub? When do I try whatever, right? So I'm looking at a random integral. How do I know how to approach it? What to actually do to figure out how to compute what I need to compute? And series, determining whether a series converges has a similar kind of requirement. Like there are a bunch of things I could try if you give me a random series. There are a bunch of things I can try to figure out whether it converges or not. And so the idea would be, when do I know what to use? When is which test appropriate? and so on and so forth. So I actually want to give you a generalized approach to when you're going in to determine whether a series converges or not. How do you know what to look for? Like, I mean, over here, when I had this, why did I know to rewrite the ln and then replace it with a polynomial and to get an inequality? Why would I even try that? Like, how would I know to try that? Or when I was like, like here, why would I think to replace the cosine with a 1, do this inequality and get a comparison? How would I know that I actually wanted to get a P series to compare this thing to, right? Like, why would I think of this? I mean, after I do it, you can probably see why it works. But the question is, how would I know to do this in the first place, right? How would you know that this would be an approach? Because this is a pretty efficient approach. Like if you were to try something else, it probably wouldn't work out. I mean, yes, technically on this one, when you got to this level, the 2 over n squared plus 1, you could do an integral test. It would have worked, but then you'd get the integral of, it'll become arctangent, then you have to take the limits. It'll actually take you a little bit longer to figure out that this thing converges. But right here, you can see it very quickly. Oh, it's a convergent P series, right? So there are also times, and this is true with integrals as well, that multiple methods can work, but one is more efficient than the other. And you kind of want to not waste your time doing needless calculations, right? So that's actually what we're going to deal with. Like, how do we know a general approach for determining series? Like the art of determining series convergence, like we had the art of integration. Because on some level, it is an art, right? There is math to it, there are calculations to it, but knowing how to approach it, what calculations to actually do at what time, that's kind of like an art, because there's no like standard approach, but there is something that can get you towards an answer quicker than later. So just like with integrals, there are some things that you kind of do right off the bat, right? So with integration, we knew that the first 3 steps are always the same thing. You always go through those steps in those order. And in the same way, we have a bunch of things here that I call the step zeros. Step 0, step 0, 0, and step 0, 0, 0. Because these are things where it's like, before you even start the problem, you should be thinking about these things, right? So I named them like step 0. It's like something that you should try immediately, right? So I give you a random series, and your goal is to determine whether or not this thing converge. Where do you start? Well, you always start with test 0, test for divergence, right? So at this point, computing a limit should be relatively easy. A lot of times you'll be able to do it just by eyeballing. You'll actually know the answer before you even start something. So test for divergence is something that you would try first. Any series, you look at it, can I see that the limit approaches 0? If it definitely does not approach 0, you're done. Your work is done. You just say, oh, limit does not approach 0, it diverges. We're done here. And you move on with your life. But if the limit is 0, then you have to work a little bit harder. So you always actually do that test first. It's quick to apply and it can save you a lot of work. So that's always the thing you want to try first for any series, always. Now, there are steps here where what you do would depend on how the problem you're trying to answer. So if I specifically ask you what a series converges to, right? Or I ask a question like, oh, determine whether the series converges or diverges. If it converges, determine what it converges to, or say to what it converges to, or hey, this series is convergent, what does it converge to? Anything of that sort. Whenever I ask you for a specific answer, what does this series add up to? Then it's only 2 possibilities. It's either a geometric series or a telescoping series, right? None of the other series tests tell us what it converges to. So depending on the problem statement, that can also hint to you what you should be looking at. So if I tell you something specific, oh, what is the answer? What is the exact answer that this thing adds up to? There are only 2 scenarios that I can ask you that in at this point. So you'll know, ignore everything except those 2 things. So that's another thing. And there's another kind of question type that would come up where, so this is step 0, 0, 0 that I'm looking at. If I ask you about absolute convergence versus conditional convergence versus divergence, then you have to use the method that I showed you in the last section. So you know you're generally going to approach the problem in this form. Okay. But of course, within this form, in step 1 and step 2, you'd have to actually know what test you want to use, right? But you'll do it in this framework. Okay. So those are just some things just right off the bat. Before you even really start the problem, you should just be aware of, right? Always try test for divergence first. Know that certain problem types make certain tests more likely than others. So if I ask you what something converges to, it's going to be geometric or telescoping. There's no other scenario in which I can ask you what something adds up to. Okay, so there is a kind of situation where something like that can happen, but that's with power series, and that's a completely different context from this. So it wouldn't be in a problem of this nature. It would be in a problem where we're talking about power series, which we might actually begin today. So you'll know what I'm talking about there. And then if I ask you about absolute convergence versus conditional convergence versus divergence, use the method that I told you earlier, which is, again, you check for divergence first, then you check for absolute convergence. If it converges, you stop and say it's absolutely convergent. If it doesn't converges, you remove absolute values and then check for conditional convergence. If it converges there, say it converges conditionally. If it diverges there, just say the original series diverges in general. And that's basically the method. Okay. So let's say we've done all that. That's all out the way. We've already checked test for divergence and we know what problem type we're in. And, you know, none of this applies anymore. So now you're looking at a random series and you want to actually talk about what would it converge to. How would you figure that out? Okay. So the first thing you'd want to do is to check if the series has a specific form that is required for a series test. So there are some forms that are required for certain tests. For example, a geometric series, it has a very special form that you need to have in order to apply the geometric series test. It has to look like a constant times a constant ratio variable, right? Or we know the other form. If we want to start from 1, it's a constant times another constant raised to the nk minus 1. This table uses k instead of n. It doesn't matter. It's a dummy variable. Hopefully that doesn't confuse you too much, right? But this is actually a very special form. If your series does not look like this, you cannot use the geometric series test. It just doesn't work. It's not going to work. It's not a geometric series. So that's a special form. Another one is like, you know, the P series test. That's a special form. Alternating series test, that's a special form, right? If you see the -1 to the end, you kind of know it's an alternating series, right? So there are a bunch of series tests where you're looking for a special form to apply that test. So something will stand out to you, like there would be a form that stands out. Oh, this is a P series that I'm looking at, or this is a geometric series that I'm looking at, or this is an alternating series that I'm looking at. There'll be a special form that tells you a test that you might want to do. So if you see one of these forms, you'll know, oh, I probably should check geometric series test, or I probably should check the P series test, or I probably should do the alternating series test because it has that form, right? The other ones don't have a general form, right? So you'll notice that the kth term test works on any series. This works on any series. This works on any series in theory, but there are some that makes it a little bit more likely than others. So, but some tests have a very special form. So the next thing you're going to look for is, are one of those forms present, right? So based on that, you will know what to look for. So again, there are certain types of series where I gave you specific names for them. You need to know those series because they're ones that you'll be looking for specifically. So I told you about a geometric series, a harmonic series, a P series, an alternating series. These are types of series that have names, but they also have forms that coincide with them. So you should know these special forms, right? Also remember, the alternating series test can only determine conditional convergence. So it cannot determine absolute convergence. So make sure you don't use that to talk about absolute convergence. Also, and I just want to point out some common mistakes. So here, for the divergence test, if limit of an not equals 0 diverges, it's very important. No conclusion otherwise. Okay. So the test for divergence can only tell you about divergence, and the alternating series test can only tell you about conditional convergence. So these should be things that you have in your mind. So if the problem asks you to talk about absolute convergence, you should know that if you're using the alternating series test, you're not checking absolute convergence. That should just be something you should be aware of. Okay. But other than that, looking for a special form is something that could help you figure out how you want to approach things. Here's another one. If a series is rational or close to being rational, you can use a comparison test. And usually in this scenario, you'd want to kind of compare it to a P series. So rational means it's a ratio of polynomials, like this guy is a ratio of polynomials. Okay. Almost rational, right? Like here I have something that's close to being rational. What I mean by that is if you ignore all the non-important terms, you can get it to look like a rational function. So we know with rational functions, the important terms are the guys with the largest powers. So the biggest guys, if you look at them, so for this, it will be like minus n squared over n cubed. You can kind of ignore everyone else. And that also tells you what you'd want to compare it to, right? So you'd compare it to the series of minus n squared over n cubed, right? Or in this case, minus 1 over n, right? And so that's harmonic, which means you can either do the comparison test, the direct comparison test, if you know the way the inequality is going to turn, or just do the limit comparison test if you don't know the way the inequality is going to turn. This one, you'll realize that this actually behaves like 1 over n, and so this will diverge. Okay. Now, the second series here, this guy, is not a rational series. However, it's close to being rational in the sense that, again, if I focus on the biggest guys, these two, right? I would end up comparing it to the series of like n squared over the radical of n to the 8th. But what is that? That's like n squared over n to the 4th, which is a rational expression, right? If I ignore all the non-important terms, I can kind of rewrite it into a kind of rational expression. And, you know, or at the very least, it's some sort of P series kind of thing. So this would behave a lot like 1 over n squared. And I know that converges, so that can tell me if this guy's going to converge. And by the limit comparison test, you'll see that this converges. So yeah, so that's something that's going to be another situation. So you can have series looking very complicated, like this guy. This looks like a monstrous series, but at the end of the day, he compares to a very nice series that you know a lot about. That's a convergent P series, and that will tell you everything you need to know. And in this case, I would use a limit comparison test with that, and you would see that that converges. Whereas the guy on the left diverges by limit comparison with the harmonic, right? So that's another scenario that you can find yourself in. So again, it's step 2 in quotes. It's not exactly the second thing you would look at, step 2 in quotations, but it is something that it's a form that you're looking out for, a rational expression or something that's almost rational. And also remember, and I'm going to mention this again later on, ratio test or the root test do not work with rational expressions. It's just not going to work. They will be inconclusive. So you wouldn't use the ratio test on guys like this. Now, here's another one. If the thing you're looking at has factorials in it or exponentials in it, you'd want to try the ratio test. It's very good at simplifying factorials, as we've seen. So factorials is something that's very difficult to work with directly at this stage. the kind of mathematical machinery we would use to deal with that is something like a gamma function, which you would learn in a higher level class than this one. And even then, it's kind of annoying to work with. So if you have factorials, you'd want to try to get away from them as much as possible. So you use like a Stirling's approximation in some higher level class, and to avoid working with factorials in directly anyway. So one thing that you can do is the ratio test, because that allows you to put an plus 1 over an. And I showed you last time that that allows you to cancel out some of the factorials and leave you with a smaller expression that doesn't have a factorial. So if it has factorials or exponentials, you should try the ratio test. So also remember, the ratio test does not work on rational functions. You'll always get inconclusive. So remember, the ratio test means you test L, which is the limit of, in absolute values, an plus 1 over an. An plus 1 and an will always be the same degree if they are rational functions, and that will give you L equals 1. Now, the ratio test is inconclusive when L equals 1. However, if L is less than 1, it converges absolutely. And if L is greater than 1, it diverges, right? And so I'll mention, remember, this test gives you absolute convergence. By the way, the geometric series test also does that. The root test also does that. So does the root test. Geometric series test. The integral test, if anything applies to the integral test. Although I don't really want to say the integral test, because the integral test, there are times when you can use the integral test to test for like, I can imagine like an alternating series where technically you can't apply the integral test, but if you put absolute values around it, then you can. So it's kind of weird. So it's integral test. But so a little bit of a caveat on that one, I would say. So yeah, if you can apply the integral test to something, you'd kind of have to ignore all the negatives to get it to work, because the integral test requires everything to be positive. And so in some sense, it's kind of like you're looking at the absolute value. But yeah, so all these tests will actually give you like absolute convergence. If they work and say convergence, the convergence is absolute, and that's actually pretty nice. Yeah, so if something has like powers, like you have a sequence term where it's raised to the nth power, it might be alternating and also raised to the nth power. But anything raised to the power of n, or raised to something like a constant times the power of n, then the root test would be a good test to use. And that's sort of self-explanatory. I don't really have to go into that. So we did an example of like a series where we had like 2n plus 1 over 7n minus 5 to the nth power. And just because you see the nth power, that kind of hinted to you that, hey, maybe a root test would work here. So the root test is the nth root, so it can reduce the nth power. And so that might be useful. It can also be useful if, say, you have like an n squared power. I guess you could actually break that down to an nth power, which might be easier to deal with. But generally, you want to look for like an nth power, or like a constant times n is the power. And then a root test would be a nice thing to use. So that thing is also kind of a form thing. You would generally tend to want to use it when you see a special form, like an expression raised to a power, and you're taking the series of that. A root test might be something that you want to try. Here's another one. And this is And this one, it's us using the integral test, but of course, you kind of have to be very good at integration to even apply this test. I guess it's something you could try if, like, by process of elimination. But you kind of want to notice that if I pretend my an was just a regular function, it would actually be something that I could integrate easily. So we did an example where it was like e to the 1 over n divided by n squared. Like, if I just imagined that as an integral, e to the 1 over x squared, I would know, hey, that's actually easy to integrate. That's just a substitution. U equals 1 over x, du is going to be minus 1 over x squared. The integral of this is minus e to the u. So it's minus e to the 1 over x. Like, I can see that in my head. It's very clear. A substitution could kill this as an integral, but it's not an integral. It's actually a summation. So whenever you see something that you could technically integrate easily, I would think the integral test. So this is an easy integral by substitution. So something could look kind of weird, kind of funny. It doesn't really fit a nice form. It's not a geometric series. It's not a P series. It's not like a rational thing. It's not like factorials in it. It doesn't like have everything to an nth power. But if this was an integral, the problem would be easy. Like, whenever you have that thought, the integral test is actually a nice test to use. You do need to remember that the integral test does have certain conditions. So if these conditions aren't fulfilled, it won't work. But these are usually easy to actually check that it's continuous. So you're not dividing by 0. There's no negatives under a radical. There's no negatives inside an ln. Right? Everything will be continuous and nice. It'll always give you positive values, and it's eventually decreasing. And remember, we know how to check decreasing. There were 2 main ways. And so once you see those conditions are fulfilled and the thing you can integrate easily, the integral test is probably something that you'd want to try. And that's essentially it. Like, every series that I would ask you, you can use like one of these tests to figure it out, whether it converges or not. And this is generally speaking when you would try which test. So test for divergence, you always try that first, know how to use it. And based on what the problem asks for, that might be a hint. So if I ask you specifically what something converges to, then it's either going to be geometric or telescoping. If I ask you to talk about absolute versus conditional versus divergence, then you know you have to use this framework here, right? Which we did some examples of. If it has a special form, like a geometric or a P series or an alternating series, that might be useful. Alternating series test does not talk about absolute convergence. So if the problem asks you about absolute convergence, alternating series test would be one of the last things you do if nothing else works out. If something is almost rational or rational, comparison would be a nice thing to do. Try to compare it to a P series. Factorials in it, use ratio test. Exponentials in it, also use ratio test, would be a good thing to try. If you have something to a power, the root test would be a good thing to try. If you see something that's kind of easy to integrate, provided that these 3 conditions are fulfilled, the integral test would be nice. And some tests give you absolute convergence automatically, and some don't. You should know what those tests are. I did mention them in the notes. So that's actually generally it. So when we were going over a general strategy for integrals, it took longer than that. So series, solving the certain problem type has a similar flavor to figuring out how to do an integral, but generally speaking, it's easier. So yeah, generally speaking, traditionally students do better on the second test than the first test, because integration, it takes more time for it to fully sink in, but hopefully series will sink in quicker. Generally speaking, the calculations you'll have to do will be easier, so that should be okay. But that kind of covers just like how we want to approach series, generally speaking. I guess we can move on if there are no questions. So this is just something to know that you should try in certain situations. Yeah, so that's how you'd approach series convergence. And you should kind of just know this table, which, you know, you do problems a few times that will actually be useful. I don't know, maybe in the summer I'll actually give you this table on an exam so you can refer to it. But yeah, that is that. So that's just generally a process of how you want to approach things. So I guess what I want to do now is talk about series estimation. So that's going to be another important topic. And it's all the way down here. Let's move you up. So this is a topic that's been spread out over several sections. So they talk about this in like 11.3, 11.4, 11.5. Right now we're at the end of 11.6. But I was kind of just focusing on the convergence tests. But now we want to talk about estimation. And I've kind of decided that, you know, in the summer, I'm going to ignore most of this stuff and really only require you to know about estimation in one specific circumstance, which is the one defined in 11.5. So in 11.5, this is where we spoke about the alternating series test. And there was a theorem called the Alternating Series Approximation Theorem. And that's kind of what I want to talk to you about in this section. And we'll ignore all the other things now. I might just mention them. I left them in the notes, just, you know, just for completeness, but you won't need to, I won't test you on them. So let's actually just worry about that. So the main topic of this section is estimating series. And the idea is the following. So I've already mentioned to you before, finding out what a series converges to is very difficult in general. And even in the nice cases, it can be very annoying to figure out what. So if it's not a geometric series and it's not a telescoping series, to actually figure out what something adds up to is very hard in general. And sometimes it can be impossible to actually calculate by hand. So the idea is we want to approximate series. We want to estimate the series. And as I mentioned, sometimes this is good enough, and sometimes this is better than actually having the actual answer. Like sometimes even if you have the real answer, you can't do anything with it anyway. You would just use an approximation if you want to apply it in the real world anyway. So it's nice to be able to work out something as an exact answer. Oh, this is exactly pi squared over 17. Awesome. How are you going to apply that in the real world? You can't. So it's just an exercise in vanity for the most part. Math people like doing that. But when it comes to like actually doing something in the real world, approximation is where it's at. And there's a lot of math geared towards approximation. So that's what we're going to do. We're going to learn how to approximate series, how to estimate them, at least in one situation. And so usually series are estimated by their partial sums. So that's going to be the idea. So I have a series. I'm adding up an infinite number of things. Obviously, I cannot do this. I don't have an infinite number of times or an infinite amount of computing power. So the idea is to just add up a finite number of things. And the question is, how many things should I add up, right? So I have an infinite sum, but maybe for my purposes, it's good enough to just add up the first 100 terms and get the answer from that, as opposed to adding up everything else. Or maybe the first 1,000 terms can do, maybe the first 500 terms will do. Like, how do you make that determination? Like, how many terms should I add up, right? Because at the end of the day, that's what's going to happen. So you can have an answer, which is an infinite decimal, non-repeating, but your calculator can only show you like 10 digits on the screen. So your calculator is only going to add up enough terms until those first 10 digits are steady, and then it's going to ignore everything else. It's not, why am I going to continue? Like, I can only produce 10 digits anyway, right? And so there's a very similar idea here. Okay, so that's Essentially, the summary is going to be this. Finding out what series converging, random convergent series converges to is difficult in general, but we can approximate it using the partial sums, add up a finite number of terms, and see how well we're doing. And series estimation theorems, these are theorems that talk about estimating with partial sums. They can tell us how good a certain approximation is, which is what you'd want to know, right? So if you can't get the exact answer, you can get an approximation. A very important question to be able to answer is, how good is this approximation? What is the error that I'm working with? Because if the error is less than something that would be practical, then I don't really care, right? So that is going to be what we're going to talk about. And the first one, so technically speaking, there were like 3 things I wanted to cover, but I'm going to skip the last 2. We're actually going to do this one, and we're going to skip this, and we're going to skip this. All right. So we're going to talk about the alternating series approximation theorem. Okay. For this, we need some vocabulary. So suppose this is a convergent series. So AN is a sum, it adds up to something meaningful. So that means it looks like this: A1 plus A2 plus A3 going on forever. So it turns out we can actually break this series into 2 parts. Right? So we're looking at this right here. Okay. So we can split it up into the first n terms plus everybody else, right? So the first n terms, we've actually seen this before. This is what's called the nth partial sum, right? You add up the first n terms, that will give you a number. That is computable. Like a computer will take a finite amount of time to do this, right? So that we can actually get an answer for. Now, to add up an infinite number of terms, that's the problem. Like, we can't have a computer adding up an infinite amount of things over an infinite amount of time. We'll never be able to get to an answer, right? So we can actually split up a series into 2 parts, like the first n terms and then everybody else. And n, of course, can vary. We can make the n bigger or smaller depending on our needs, right? So the vocabulary is the first n terms. This is usually denoted S sub n, and it's called the nth partial sum, right? And this is just the sum of the first n terms. Everybody else is called the nth remainder term. Everyone after the nth term onwards, this is called the nth remainder term, and it's usually abbreviated by big R sub n. Okay, so when I say remainder term, that's what I mean. I mean the tail end of the series, right? The infinite amount of terms after we add up the first n terms. This is called the remainder term. Okay, so that's just like a definition here. So you should just know that. That's what a remainder term is, right? So if I add up, I have a series that looks like that. The nth remainder term is that expression. It's from the n plus first term plus adding everyone up, going all the way back. Okay. Now, one thing you can notice is that, of course, your series essentially means your series, which is S, can be thought of as Sn plus R sub n, which means that you can think of Rn as S minus Sn. Or we can just think the magnitude of the remainder term, how big the error is as a magnitude, is just the magnitude of that, right? So that leads me to this definition here, right? If this is a series that adds up to S, then the remainder term, the absolute value of the remainder term, is the same as S minus Sn in absolute value. And this is talking about the error in the approximation. So the remainder term, the magnitude of the remainder term is called the error in the approximation. Okay. So whenever you're approximating a series, one thing you're going to want to add to that is, oh, this is an approximation. This is the error. We can be wrong by this much. We can be off by a half, or we can be off by 0.001. We can be off by 15 digits. We can be off by 1 digit. There's going to be a measure of how much you're off by, right? That's going to be very important. Now, it turns out in a very special case, there are many special cases, but the one we care about is in the case of the alternating series. And this leads to what's called the alternating series approximation theorem. So this is very important. This is definitely something you're going to be tested on. So that you should know. Okay. The important thing for the alternating series estimation theorem is this line right here. It actually tells you how big the remainder term is going to be, right? So this will tell you that in the event that you have an alternating series and you add up the first n terms and then you ignore the rest, you are going to get an error from ignoring the rest. The alternating series approximation theorem tells you the magnitude of that error is actually from the nth plus first term, which is, it's actually very nice how that works out. It's a very nice theorem. So the n plus first term will actually tell you how close the sum of the first n terms is to the actual answer. Okay, so we're not going to look at the proof of this. It's not important. But knowing that fact is going to be very important, and I'm going to require that you use that fact. On top of that, we actually know that the error, the remainder, which is without the absolute values, it will be the same sign as the n plus first term of the unused series. So when I say the first unused term of the series, I'm talking about the n plus first term, right? Whatever sign that has, that is going to be the magnitude of this. So if that is negative, it means our partial sum was bigger than the actual answer. If that is positive, then our partial sum was smaller than the actual answer. So that can actually tell us, oh, here's the error, and I know exactly what direction it goes in. I know I can be bigger by this much, or I will know automatically that I can be smaller by this much. So my error, it gives you a window for the error. And so that's pretty neat. But yeah, it turns out that you can actually look at an alternating series in this way, which is, it's very convenient, it's very nice, it's very unique among series. Okay, so let's say I add up the first 10 terms and I asked you, right, instead of adding up infinite number of them, I just add up the first 10 and I ask you, how good an approximation is these 10 terms for the entire series? Then what you do is you would look at the 11th term. How big that 11th term is the error itself, which is very nice, right? So just look at the next guy. How big that is tells you how far off you are. And if that sign is negative, it means that you are actually bigger than what the actual answer is. You're actually a little bit above it. And if that term is positive, you're actually smaller than what the actual answer is. You're actually a little bit below it. And it can tell you by how much. So that's very, very nice with this series. So with alternating series, it's very easy to approximate them or estimate them. And so let's actually do an example. So here is our alternating harmonic. This is a guy that we've actually seen before, right? So it's like 1 over n, but it changes sign, right? So we know that this guy looks like -1 plus a half minus a third plus a fourth minus a fifth plus da da. Okay, so we have that, right? So now this example says find S4. So we remember our notation. S sub n means the sum of the first n terms, which means S sub 4 means the sum of the first 4 terms. So because this is an alternating series, I know that S sub 4 is going to be equal to, well, the first term plus the second term plus the third term plus the fourth term, because it's alternating, right? Now, I'm not going to necessarily write out, you don't really have to write that line, but you should just know you're just adding all these terms. So the first term was a -1, the second term is a plus a half, the third term is a minus a third, the fourth term is a positive a fourth. That's it. And so now we can actually write down what that is. I guess 12 is the LCD. So it's like minus 12 over 12 plus 6 over 12 minus 4 over 12 plus 3 over 12. This is minus 7 over 12. Right? And this is okay. So that's it. But just for comparison's sake, this is 0.8, no, 0.5. This is 0.583, and the 3 repeats forever. Okay, so that's what the sum of the first 4 terms adds up to, minus 7 over 12, right? Which is about minus 0.583. Okay. So now, that was part 1, right? Just find S4. Okay, cool. So now is another question I could ask you here. How good an approximation is S4 for the series? So I ask you to find the sum of the first 4 terms, and then I ask you a question. If I were to just run with this as the answer, right? If someone were to ask me, what is this sum equal to? And I said, it's about minus 7 over 12, right? How close would I be to the real answer? Okay, so this means what they're asking me about here is the magnitude of the error. Now remember, that is simply the magnitude of Rn. It's the things that I left off other than the sum of the first n terms. So in this case, that is going to be, you know, the remainder, the 4th remainder term. What happens after the first 4 terms? Now we know by the alternating series test is that this is going to be, well, we actually know this by the definition. This is actually defined as S minus Sn, where, or in this case, S minus S4, where this is the actual answer. And this is the 4th partial sum. Used to approximate the answer. Now, according to the alternating series approximation theorem, that expression is less than or equal to the an plus first term. So this is going to be less than or equal to A5. This is true by the alternating series approximation theorem. But what is A5? Well, the 5th term, right, after 1/4, the next term is obviously going to be minus 1/5. So this is actually going to be 1/5. Right? So that's literally 0.2. So, i.e., Rn equals S, say R4. R4 equals S minus S4 is going to be less than or equal to 1/5 or 0.2. And that's going to be our error. And I mean, any okay, so any questions so far, like on me using this theorem, or me doing any of these calculations? Okay, Let's move on to the next part. So I'm given this series, it's an alternating series, alternating harmonic series. We calculated the sum of the first four terms. The error we've also just calculated. It's just the magnitude of the fifth term, which is 1/5. Is S4 larger or smaller than the actual sum? So this is just a question of measuring, is our first partial sum higher than the real answer or smaller than the real answer? And this, again, it's just a matter of looking at the sign, right? So the sign of the fifth term is negative, right? Because if I continued this pattern, it will be minus A5, minus 1/5. You can see it right here. So this would mean the sign of S minus S4 is also negative. Right. We have this as a consequence of the alternating series approximation theorem. Like you don't have to know why that is, just know that that is the case, right? The sign of the n plus first term is also the sign of the difference between the two. And if S minus S4 is negative, it means that S4 is larger. So S4 is actually minus 7/12, which is like minus 0.58. This is actually bigger than what the real answer is. That's what we know already. We also know that not only is it bigger, but it's bigger by as most 0.2. So the actual answer will be anywhere between minus 0.5 and minus 0.7 is essentially what we can discover just from doing these very simple calculations. Right. I did mention this, so later, and I will actually prove it to you. We'll see that this series is equal to, it's actually minus ln2, which is a very strange thing to be, which, by the way, is actually about 0.7. It's 0.693147. I actually I wrote out a few digits. 314,718, blah blah blah. So it is around 0.7, which is actually pretty cool. And so, yeah. So my so the S minus Sn is actually was about 0.10981, which is of course less than 0.2. So we actually know what this actually adds up to, and it falls in line very nicely with the calculations that we're doing here. We're like a little over 0.5, almost 0.6. We know we're about 0.2 off. We also know that this is bigger. So the guess would be we're around minus 0.7. And it turns out that that is actually true. So I thought just showing you the actual numbers, that would be pretty cool. So it turns out we can actually know how good we are to the actual answer. So that's actually a big error, all things told, all things considered, but it's actually something that we can know what the error is and figure that out. So another question is, how would I want to, let's say we actually know what we want the error to be, right? So let's say I know I have a calculator that can be only accurate to this many digits, or I know that I have a machine that's going to build something in real life, and that machine is only accurate to this much. How many terms would I need to get that level of accuracy, right? That is a question that you'd want to ask, right? What if I don't want to be off by 0.2, I want to be off by something smaller? So here we're asking the question, what if we want to be off by 0.01, right? I want to be within 1% of the actual answer, right? 0.2 means I'm within 20% of the actual answer. That's too big. A 20% error is too much. What if I want the error to be 1%, right? I want to be within 0.01% accuracy, okay? Like how many terms would I need? So here's the thing. So we know the alternating series approximation theorem, or by the time it comes around to being tested on it, we will know the alternating series approximation theorem. And we know that the error is going to be given by the n plus first term. So we can actually use this to our advantage, right? We know by the alternating series approximation theorem that the error is going to be s minus sn, and we know that this is less than or equal to the an plus first term. So what that means is we want the an plus first term to be less than 0.01. That's all we want, right? If we can keep going until the an plus first term is less than the error that we want, then our alternating series, the nth partial sum of our alternating series, will be good enough for our answer. So we can actually do that. By the way, this might be nicer. It's actually 1 over 100. Okay, so here, of course, our an is 1 over n. So that means your an plus 1 is 1 over n plus 1. And that means we want 1 over n plus 1 to be less than 0.01. Or we want it less than 1 over 100. So this, of course, means that n plus 1, we need to be greater than 100. Which means n needs to be greater than 99. So that tells you how many terms we need. We need 100 terms to have the desired accuracy. Adding up an infinite number of terms, impossible. Adding up 100 terms, the average computer today could do that in a fraction of a second. It's not a big deal. So it turns out, if I want to be within 0.01 of the answer, meaning I want you to add up until we get like minus 0.68, how many terms would I need to add up to get that close to the correct answer of minus 0.69? I need 100 terms, which for a computer is nothing, right? So I can know that I'm not getting the real answer, but I can control how close to the actual answer I get, right? And again, if I wanted to be within 1,000 terms, I can just solve this equation for 1,000. But if I wanted to be good up to 6 decimal places, I could solve that equation and figure it out. So I can always change this equation to figure out how many terms do I need to add up. And we're at the stage now where a computer can add up 1 million numbers in a second, less than a second, right? So we have processors working in like terabytes now. Like we need kind of 100 trillion numbers in a second. Probably not with your laptops at home, but you get the idea. Like adding up numbers is not a problem for a computer. And yeah, so being able to add up 100 things instead of an infinite number of things, it is a big win. It's like less than a second of work for not even a good computer. Like you can use a horrible computer and actually do that relatively quickly. So that's actually pretty cool. Now, your book actually talks about making approximations for the integral test. If you know something converges by an integral test, you can determine the error. If you know something converges by a P series test, you can actually determine the error there. We're actually going to skip this, so I put ignore in the notes. So I'm not going to require this. I might ask about it in like a bonus problem or something, but you don't have to know that. This is the only one you need to know, the alternating series approximation theorem. And it's a pretty easy thing to do. So the n plus first term tells you how close the sum of the first n terms is. The sign of the n plus first term tells you the sign of the error. So if it's negative, it means you're larger than the real answer. If it's positive, it means you're smaller than the real answer. And you can actually determine how many terms you need to get a certain error by setting an plus 1 less than that error. And then you just solve that equation for n, and it will tell you how many, what size does your n have to be. That tells you how many terms you need to add up to get to that level. So yeah, we have that. And that kind of ends our discussion on estimation of series. Like there's only one scenario I'm going to ask you to estimate series in, where I'm like, okay, we don't know the real answer, but get me close to this answer. Tell me how close we are. Tell me if we're bigger or smaller. And what if I wanted this to be the error? How many terms would I need? These are questions that I can ask you. And in the case of the alternating series, it shouldn't be difficult. Like there's no calculus here, right? It's just solving inequalities. And we won't do that. So we're going to take a break, and then we're going to come back and talk about power series. So I won't get much beyond the definitions of our terms here, but then we'll hit the ground running tomorrow with some examples. But for now, we're going to take another break, and we're going to come back and talk about power series. So we'll take a quick 5-minute break. Not much to. I'll leave it here. All right, I will see you guys in a bit. All right, we are back. Okay, yes. All right, we are back. So we just spoke about, well, we spoke about a lot of things. Absolute convergence versus conditional versus divergence. We spoke about how to approach series convergence problems in general. And we spoke about estimating alternating series using the Alternating Series Approximation Theorem, which actually has a lot of information packed into it. We can know how good an approximation is the sum of the first n terms is for an alternating series. We can know if our approximation is bigger or smaller than the real answer. And we can actually control the level of accuracy we want by solving this equation, an plus 1 less than the error. There are a couple more things. We're going to ignore those for now. We're moving on to 11.8, which is talking about power series. Now, power series. I am trying to think if there is a more important use for series. Like this is why series are, it's one of the main reasons why series are useful. It's like one of the biggest things. Even in very, very high level mathematics, one of the considerations of, wait, can I write this thing as a power series or a certain type of series that is similar to a power series is a very common question to ask. They can simplify a lot of things for us, and it's really, a power series is a really nice thing. And it turns out that when you can write functions, for example, as power series, it gives you a lot of powerful machinery to help you, and a lot of things work out that wouldn't work out otherwise. It's a really big deal. So power series, really big deal. It's sort of like a new topic, but at the same time, it's kind of like learning about an application. It's an application of series. So this special kind of series is just very widely applicable. And a lot of things in mathematics work out if we can actually get a power series to fit in there somewhere. And so, yeah, power series, a very good thing. We are just a few, a little over 20 minutes left in class, so we're not going to get really far with this, but at least just to set the stage, I want to tell you about some definitions, talk about some theorems, maybe like give you some general ideas or concepts that would apply to a power series, and we will be satisfied with that and call it a day. So this is the definition of a power series. Okay. So a power series is any series that looks like this, right? So if you look like this, we call you a power series. More specifically, we call you a power series centered at x naught. Right? So that's pronounced x naught, x0, you know. But x naught is what we usually refer to it as. So Cn is a constant. So I'm mentioning what the parts are here. Cn is a constant. X is just a real valued variable. In higher level mathematics, it might be thought of as a complex variable. And x naught is another real number, but it's constant, right? So the x can change values, but the x naught can't. We think of that as constant, and that's what the series is centered around. Now, why is this series so important? So what we can do here is we can actually just write out a first few terms of what this guy would look like, right? So if I actually went in and I plugged things in, plug in n equals 0. So this would look like C0, x minus x naught to the 0, which just comes out off as 1. If I plug in n equals 1, this would look like C1, x minus x naught to the first power. Plug in n equals 2, it's like C2, x minus x naught to the second power. Plug in n equals 3, C3 x minus x naught to the third power, and so on and so forth, right? Okay, so that's the kind of expression that we're looking at, right? And this goes on forever. And you might not necessarily see what this reminds you of right off the bat, but it's very close to something that it should remind you of. So if I were to plug in x naught equals 0, right? What would that look like? Right? So here's the series when I plug in x naught equals 0. So it would look like Cn x to the n, and let me write out some terms here. So when n equals 0, this looks like C0. When n equals 1, it's like C1x. When n equals 2, C2x squared, C3x cubed, C4x to the fourth. What does that remind you of? Does that remind you of anything? What kind of formula is that? What are they called? Do you know the name? Do you remember the name? So this looks like something called a polynomial, right? Very important functions, but it's you'll notice that this will keep counting forever. So you get x to the 5th, x to the 6th, x to the 7th, x to the 8th, and it just keeps going. So it's kind of like a polynomial of like infinite degree, right? Which is not generally speaking in the definition of a polynomial. We always talk about nth degree polynomials. So there's a highest power. So this here is a series that essentially when you expand it, it looks like a polynomial, but the degree keeps going up. It's an infinite degree polynomial. It's like an infinite sum, an infinite length polynomial. And one thing you will notice, or hopefully by now you realize, polynomials are very nice. We know a lot about polynomials, and a lot of things that we like doing, they're super easy to do with polynomials. Polynomials are easy to take limits of, they're easy to differentiate, they're easy to integrate. They're continuous everywhere. Like all the nice things that we would want in a function, a polynomial has them. So if we have something that, we have a series that sort of behaves like a polynomial, it's going to be a very convenient thing to have. And on top of that, let's say we can determine that this series, I don't know, converges absolutely in some sense. then it's a bona fide mathematical object. In some sense, I can kind of treat it like I would any other function. And this is a function that sort of looks like a polynomial. And that means we can do a lot of things with it. And it will behave very nicely as we're doing it. Now, the name power series, it comes from the fact that x to the n is called a power function. Right, that's just the name of it because x to a power. And so because it's a series that looks like a sum of power functions, we call it a power series. So that's where the name comes from. Okay. Now, these are basically power series are a series that looks like polynomials. They're infinite degree polynomials. And we're going to talk about some consequences of that soon. But before that, let's talk about a very, very important theorem. So there's this theorem. Now, because this is a series, we can talk about the convergence of the power series, okay? And it turns out that there are three possibilities when it comes to the convergence of power series. So if I have a series, it's a sum that looks like this form. And we can talk about, does that series converge? And it turns out that there are three possibilities for the convergence of a power series. So one possibility is that the series converges only for one value of x. Namely, if we set the variable equal to x naught, it will converge like that. And you'll notice in this formula, if you set x equal to x naught, you pretty much get 0, right? So you'll have C0 plus a bunch of zeros, and that obviously adds up to C0. So that would obviously converge and give you a finite real number. And so we will be good. Another situation is the series will converge for all real values of x. So if I look at this series, it's possible that no matter what I plug in for x right here, this sum will make sense. It's going to add up to something meaningful, and I can actually use it. And it turns out that it's very possible, and it turns out that when I have that convergence, it will converge absolutely. So that's actually pretty nice. A third possibility is that it doesn't converge for all real numbers, but there's an interval on which it converges absolutely, given by this kind of expression. And this is why it's called centered around x naught. So it's all points that are within a certain distance from x naught, right? So this describes an interval, right? So remember x minus x naught less than r. If you rewrite this without absolute values, this is what you would get. And so it's like all points that are within our distance from x naught. And so this would sort of look like it's like an interval where there's an x naught right here, and you're looking at all x values that show up if I move r units away from x naught. And outside of this window, it won't converge. But inside of that window, it will converge absolutely. And the actual endpoints might be included, like this could be a square bracket or whatever, but that's not something you would know ahead of time. That's something you have to check extra. But within this interval, it will converge absolutely. So you will notice one important thing, one nice thing about power series, it's already having some nice properties. It always converges. There's always a place where it will converge, right? You'll never have a power series that diverges everywhere, right? It's not going to happen, right? It will always converge. There are just three possibilities. Either it converges at a single point, it converges on the entire real line for all real numbers, or it converges on an interval, right? Now, this interval that we converge on is called the interval of convergence. And the length, this r distance here, is called the radius of convergence. So these would be things that it's important that you know these expressions, because these will be things that I will ask you to find, right? Find the radius of convergence, find the interval of convergence. These are things you should know what they're called because you'll have to find them, right? So, and here is where I expanded the absolute value to talk about what the interval would look like, but we already knew that. And case 3 can have several scenarios. So like I said, the endpoints may or may not be included. So you could have like an open interval or a half open interval where the left side is closed, but the right side is open, or you can have the right side closed, the left side open, or you can have both sides closed. Like whether or not you're closed, you won't know ahead of time. It's something that you will check for afterwards, right? So that's an important thing. Now, again, in case 3, these guys are called the intervals of convergence, right? These are possible intervals of convergence. So these I would abbreviate as like IOC, intervals of convergence, which is like also ROC stands for radius of convergence. So that's just some shorthand. Okay. But a power series will always converge somewhere. And whenever it does converge, it converges absolutely, which is really nice. So this thing that looks like an infinite polynomial, whenever it converges, I can essentially treat it just like I would a polynomial, which is very nice. It actually adds up to a finite value that we can actually do calculations with. We can do calculus with it, all that good stuff. Now, so the interval of convergence for a power series is given by that. And the endpoints of this interval may or may not be concluded. R equals 0 is possible, which, I mean, if you directly plug it into this this inequality here, it doesn't really make sense for an absolute value to be strictly less than 0. But R equals 0 really describes case 1. Right? So that means your x would have to equal x naught, and it won't work otherwise. R equals infinity is what describes case 2. So this length here can go off to infinity, which means it covers the entire real line. Every real number would be covered. And so I just made some notes here, right? R equals 0 means there is no interval. Technically, it converges at one point. If R equals infinity, it converges everywhere. And so that's the idea. And so we can have a series. So if to illustrate, given this series, right? The possibilities for where it converges, possibilities for convergence. So case 1 says, on the real line, there's the point x naught, and it converges only for x naught. Series only converges here. Everywhere else, it doesn't make any sense. In this case, the radius of convergence is 0 because it's not an interval, it's just like a specific point. And your interval of convergence is just, essentially it's undefined because it's not an interval. Right? It's kind of equivalent to just a set with a single number in it, which we know is not an interval. An interval will have an infinite number of things in it. So that's the first situation. Your power series will make sense only at this specific point. Once you move from that point, it doesn't make sense anymore. It adds up to infinity. It diverges. Another situation is on your real line, your x naught is here, but it works everywhere. Right? Series converges absolutely no matter what x we plug in. Now, in that case, that means your radius of convergence is infinity, and your interval of convergence is going to be the entire real line. That's a possibility. Okay, so that's another situation. Now there's a third situation. Where you have this guy, you have your x naught, but it only converges up to a certain point. So there's going to be a distance that it can move to the left or the right from x naught, where x naught is going to be exactly in the center. So this is like r equals k. And inside here, the series converges absolutely. Outside, it does not, right? But inside, it makes sense, right? And this window opens up to x naught plus k. This one goes down to x naught minus k. So the series converges absolutely in this interval. Right? So in this case, if I were to ask you, you would say the radius of convergence is k. The interval of convergence is going to be x naught minus k up to x naught plus k, where the endpoints may be included. You can say where each endpoint may or may not be included. Need an extra check. Need extra checks to determine. Technically, this appeared to be insane. Okay. So that is a power. This is what a power series is. It's kind of like an infinite degree polynomial. And this is talking about the convergence of a power series. They will always converge absolutely in some sense. The difference is it'll actually happen at exactly one point, or it can happen on the entire real line. No matter what I plug in x for x, this is going to work. Or it can so happen that it will only work for a certain amount of x's that are on a certain interval. So within that interval, it will work. Outside that interval, it won't work. Now, the question might be, how would you go about finding a radius of convergence or an interval of convergence? And the answer for Calc 2 anyway is use the ratio test. You would always use the ratio test. Always use the ratio test, right? So that's the nice thing about Calc 2, right? We're only going to ask you about a situation that's very easy, where if I say, find the radius of convergence or interval of convergence, what are you going to do? Ratio test. Always the ratio test, okay? You're never going to try to do anything else, right? So it's either going to be a ratio test, or you're going to use some fact that you already know because we used a ratio test earlier, right? But it's always going to be through the ratio test. And why is the ratio test actually useful? Because the ratio test actually has a very nice, it introduces like this absolute value less than something naturally. So you might say, why ratio test? Right. So the question is, in the ratio test, you would want L equals to like the limit as n approaches infinity of Cn plus 1 x minus x naught to the n plus 1 over Cn x minus x naught to the n. And you want this less than 1 for convergence. Okay. So that sort of means that you need the limit. Well, it's Cn plus 1 over Cn. This will just be x minus x naught less than 1. And so you would have x minus x naught less than 1 over the limit of this guy, Cn plus 1 over Cn. So you have this x minus x naught less than or equal to some constant, just naturally, right? In the event that this actually converges, this is what it's going to converge to. And it turns out you're going to be in a situation where this is never going to be 1, and it's never going to be inconclusive. You're always going to be able to actually determine it. And we'll actually see that later. So in the event that well, we'll talk about that later. So so you see an interval naturally arises. The same is true for the root test, but the root test is kind of weird. The nth root of something, it's very hard to actually calculate what that is. But yeah, so for the to determine when an radius, to determine the radius of convergence or interval of convergence for a power series, we're always going to do the ratio test because it gives us an interval right away, and we know convergence here means absolute convergence. The root test would give a similar answer, so that's why we just go with the ratio test, because it works in more scenarios. So what you can do, I won't worry about these formulas too much, but actually try this on this example. Did I give any other example? I think I gave several. Yeah, so I gave you several examples here to try, so I will leave them for you to try, and that's another section, but we'll get to that next time. We're going to stop there. Theoretically, for now, that's all we need to know to actually do this problem. And it's a very important problem type to learn how to do. Given a power series, find its radius of convergence and interval of convergence. But we'll stop there. Try these out for tomorrow, and I will see you then. As you know, like I said, tomorrow's the last day to withdraw or change your grade type. So you might want to talk to me before you do that, or maybe you've decided after looking through your report that you won't need to worry about that right now, but just so you know. But for now, I think that's what we will do. So have a good night. Try these problems out. I will see you guys tomorrow in the next one. Ciao.